It is my great pleasure to present our work, iCellSpeed, an on-device solution to increase cellular data speed via device-assisted cell selection. Increasing user access speed is one main driver behind the cellular network evolution. Operators have been heavily and continuously investing and upgrading their network infrastructure. They acquire wider radio spectrum, deploy denser cells, and migrate to advanced technologies, say from 4G LTE to 4.5G LTE Advanced and to 5G New Radio. In one word, they enhance raw system capabilities to offer users higher speed. In this work, we find in today's cellular network, raw network capabilities is often underutilized so that the data speed a mobile device got is much lower than what it could have been able to get at best. We argue that it is equally important to exploit the existing network capabilities. In today's cellular network, a mobile phone at any location is often covered by a number of cells nearby. Each cell can be used to serve the device and provide radio access, but selecting different serving cells could lead to distinct data performance. As a result, the mobile device may miss higher data speed if the cell selection is not proper. Let's explain it using a real-world instance. At one place at Purdue campus, we observed that, by default, the phone was served by cell A and got 4.6 Mbps downlink speed on average. But what if the phone was not served by cell A, but by another cell? We observed that the phone could get 49.3 Mbps immediately if cell B was used. This indicates that at least 10 times data speed is missed. Network capabilities are largely underutilized. This is not a corner case. Such data speed miss is repeatedly observed at this location. Here, in 40 pairwise runs, we found that the default operation chooses cell A and gets data speed no higher than 10 Mbps. In contrast, the device could get a much better speed if not using cell A when our solution is used. The observed performance gap ranges from 29.3 Mbps to 60.6 Mbps, up to 15 times data speed missed. We have similar observations at many test locations for all 4 US carriers. They will be detailed in our evaluation. Why are good performance missed? It turns out that the legacy cell selection should hold accountable. To explain why, we first introduce the background on legacy cell selection. The legacy cell selection is typically performed in 4 steps. First, the serving cell configures the condition for the device to measure and report radio signal quality of candidate cells. When the conditions are satisfied at runtime, measurement and report are performed. Upon receiving reports from the device, the network, that is the serving cell, decides to hand over to another cell if another cell is better. Note that measurement and reporting are triggered only when the pre-configured conditions are met in practice. For example, the device measures the radio signal of other cells when the serving cell's RSRQ drops below -15 dB, or RSRP is weaker than another threshold. The device sends a measurement report back to the serving cell if there exists a cell which is 3 dB stronger than the serving cells. When these conditions are not satisfied, cell B will not be measured, or the measurement result will not be reported, and thus no handoff happens. To better understand cell selection, I would like to introduce another technology called carrier aggregation, which makes cell selection more complicated. Carrier aggregation is enabled in 4.5G LTE Advanced and beyond to boost the data speed. It allows more than one cell to serve the mobile device. There is one primary cell, which is mandatory, and there are several secondary cells, which are optional. Each cell runs on one frequency channel, which is associated with distinct central frequency and channel bandwidth. Each channel belongs to one LTE spectrum band. Here, the left table shows the LTE bands used by 4 US carriers. Each band has their own bandwidth and covers multiple channels associated with different channel bandwidth. For example, band 2 is wider and thus accommodates channels with 5 MHz to 20 MHz, while band 5 is much narrower and offers only 5 or 10 MHz channel bandwidth. This leads to the diversity in today's cell. Now, let's go back to the previous instance to illustrate how the legacy cell selection should take the blame. We examine the set of serving cells used in these 40 pairs and show the set of serving cells. Each set is represented by one primary cell and at most 2 secondary cells. Each cell is represented by its channel number followed by its physical cell ID. So here in run A, we can see that only one serving cell A is used without carrier aggregation. It operates on channel 2425 with cell ID 363. While in run B, when our solution filtered out cell A by disabling band 5, we found that other sets of serving cells with carrier aggregation enabled will be selected to serve the device, and thus increase data speed. Here, we can see 3 different serving cell sets are more commonly to be used. For example, the first set uses 2 cells, one operated on channel 5145 in band 12, and another cell operated on channel 850, which is in band 2. So why does cell selection choose the poorly performed cell at run A and not choose other cells which can provide higher speed? Now, let's go into detail and explore why cell 363 is selected. One thing we notice here is that this cell has quite strong radio coverage around this location. Its RSRP is higher than -100 dBm, and its RSRQ is largely higher than -15 dB. It is comparable and even better than other well-performed cells, like cells over channel 850 and channel 5145 with cell ID 16. There are several reasons for the selecting of cell 363. First, the legacy cell selection relies on radio quality comparison but ignores non-radio factors which could impact data performance, such as channel bandwidth. This is a 125-meter walking trace towards the test location. At the start, cell 363 has a stronger radio and thus beat down the other 2 cells. Regardless, both other 2 cells have wider bandwidth, which likely can provide better performance. Second, the legacy radio-based cell selection discourages leaving the current cell, although other cells have stronger radio signal quality. Here we can see cell 16 over channel 850 is stronger than serving cell 363 when the device moves closer to this test location. But no handoff to cell 16 happens, because cell 363 configures the mobile device to measure any cells operated on other channels only when its radio signal drops below -15 dB for RSRQ or -122 dBm for RSRP. In this instance, such condition is not satisfied, and thus no measurements over well-performed cells like cell 16 are performed. Third, the existing cell selection not only discourages leaving the current cell, but also limits the scope of candidate cells to be considered for handoff. This makes our cell selection become local optimum. In this instance, once cell 363 is selected at the beginning, other interfrequency channels are not measured if its radio quality is not too bad. In other instances, even if the measurement condition is satisfied, other reporting conditions can also limit the cell selection result. Last, I would like to highlight another drawback of today's cell selection, that is, not making full power of carrier aggregation. Actually, in this location, not only the previously listed 3 serving cell sets are used. We observed more than 19 different serving cell sets. This figure shows the performance and the frequency for each serving cell set. We can clearly see the last set, 19, is poorly performed without carrier aggregation enabled. But sometimes when carrier aggregation is enabled, like here, set 6 by the same primary cell, the performance is much better. Unfortunately, carrier aggregation is not enabled all the time, as it is limited by the current implementation at the network side. So how can we solve this? Particularly without requiring any changes at network side. We propose iCellSpeed as our solution. We add additional component at device side atop of the legacy cell selection procedure. This added component is called iCellSpeed. The core of iCellSpeed has two extra steps. First, challenge the existing cell selection result. Second, if the challenge fails, no changes are made. If the challenge succeeds, the device takes further action to affect reporting, namely device input for the cell selection, and thus indirectly influence the cell selection result. iCellSpeed challenges the existing cell selection result when the performance of serving cell is poor, and there exist other bad choices. This is done by monitoring performance and comparing it with historical performance profile. iProfile is the component that maintains and updates the historical network performance profile. We use crowdsourced measurements to build the initial profile and use an algorithm to quickly update it with runtime measurement results efficiently. Except keep monitoring and updating the network performance of each serving cell set at one location, it also provides profile including the availability of serving cell sets at this location and the frequency of each set to be selected. iCustomize takes the network profile input from iProfile and challenge the performance of current serving cell according to speed not OK rules. These rules compare the current network performance with historical profile and see whether the speed is OK or not. We devise intuitive rules such as current performance is no worse than a portion of the best, for example, above 70% of the 50 percentile performance of the best serving cell set, or current performance is above a certain percentile, for example, the midpoint of the performance range. Here, we propose 4 different rules. Rule 1 is the most conservative one, and Rule 4 is the most aggressive one. iCustomize uses these 4 rules as a tuning knob to balance speed gains and the missed rate. Due to the device-side limitations, iCellSpeed cannot select the cell directly. There are only 3 options available: lock band, block bands, and a reset network. iCellSpeed assesses potential benefits of each possible action and picks the one with the highest gain prediction. Please refer to our paper for more details about how we do the assessment. This completes our design for iCellSpeed. Next, we present our evaluation results. We conduct large-scale measurement study at 4 US cities, mainly at West Lafayette with 4 US carriers. Our datasets are publicly available at GitHub. We first check how badly can network performance to be missed in reality. To answer this question, we keep downloading a large file from our local server while driving along every single road at West Lafayette, forth and back. We divide each road into many small grids and then quantify the performance gap between the best serving cell set and the worst serving cell set observed in each location grid. Our measurement result shows that there are more than 20 Mbps absolute performance gap at more than 55% of location grids for AT&T, Verizon, and Sprint. We can observe at least double the data speed at 50% of location grids. Next, we evaluate the speed gain in static test. Here is the result at 24 locations randomly selected in 4 cities with heavy file downloading. We observe iCellSpeed increased the median data speed larger than 10 Mbps at 19 out of 24 locations. The median relative gain is larger than 100% at 15 out of 24 locations. We further evaluate the game on real applications. Here, we show two 4K video streaming experience at one test location without and with iCellSpeed. As we can see, iCellSpeed significantly reduces stalls and offers much better and smoother watching experience. We have similar games at other test locations. iCellSpeed greatly reduces the stall overplay ratio. iCellSpeed also benefits dash video streaming with various bitrate. It achieves significant performance gain at many test locations. It allows video player to select higher bitrate and provides much better video streaming experience. 4K is much more commonly used when iCellSpeed is deployed. While without iCellSpeed, the video was usually played with much lower bitrate. And for Zoom video conferencing, iCellSpeed helps to reduce delay. For example, at one location, the latency of Zoom conference call is greatly reduced for both uplink and downlink. And for bulk file downloading, the downloading time can be reduced with 3 to 4 times with different downloading file size. Note, iCellSpeed only boosts the application with elephant flows which care data speed. For mice traffic, iCellSpeed will not be triggered as the flow ends shortly. We also conduct evaluation on driving tests. This figure shows an instance of one driving round at West Lafayette. iCellSpeed takes effect at around 450 meters when it detects the network performance is poor, and it greatly improves the network speed. We calculate the performance gain between iCellSpeed and default network performance. In other driving roads, we also see high performance gain when iCellSpeed is triggered. The average performance gain ranges from 97% to 275% in 6 roads at West Lafayette. We next evaluate how iCellSpeed performs in a multi-user scenario. We use 5 co-located phones and enable iCellSpeed on several phones amongst them, from 1 to 4. We consider in 2 scenarios. The left one has all the tester phones initially served by poor cells. The right one has only those phones running iCellSpeed to be initially served by poor cells, and other phones are served by good cells. We clearly see that iCellSpeed boosts performance for phones previously served by poor cells in both scenarios. In the right figure, the phone without iCellSpeed gets its speed dropped when other phones switch to the good cells. This is expected because iCellSpeed is to exploit underutilized capabilities, but not to increase raw capabilities. Once more devices move to the good cell, they compete resources, and thus the obtained share drops. We conducted extended evaluation, including results for other carriers, micro-benchmarking for iCellSpeed components, disruption and energy overhead, and a reality check for cell deployment density. Please refer to our paper. To conclude, in this work, we conducted the first study to unveil the missed performance problem, and we proposed the first device-side solution to solve this problem with limited on-device power. Our work revisits legacy cell selection solution, which underutilize new capabilities of modern cellular network. iCellSpeed has 2 meanings. First, it increases cellular data speed. Second, iCellSpeed uses eye-assisted cell selection to increase data speed for the device and by the device. Thanks for watching.